Hello, this is lecture 19 of the final week. Today we're going to finish simple linear regression. Tomorrow we're going to do Bayesian statistics. I'm moving our final review from Tuesday to Monday, 9 to 11 in our usual room. On Tuesday you'll have extended GSI office hours. Our final will be Friday from 9 to 12 in our classroom. So last time we talked about a 95% confidence interval for beta 0 and beta 1, and now we're going to take this a bit further and talk about the standard error for the regression line. So let x be a point on the x-axis and y paired with x. So this is a particular x-y pair. And so you can write y as beta 0 plus beta 1x plus an error term. And so the expectation of the error is 0, so the expectation of y is just beta 0 plus beta 1x. So the expectation of y is the expected y value that you get for a particular x on the Tyche line, right? So we write expectation of y is beta 0 plus beta 1x. We'll denote x as x on a regression line as y hat. And so sort of illustrated that here. So a particular x and the predicted y written as e of y on the Tyche line, and y hat our estimate of e of y on the regression line. And then also y is at the top here, right? So here I just show you that the expectation of y hat is the expectation of y, right? So e of y hat is beta 0 plus beta 1x, which is e of y. And then I just write out another expression for y hat as y bar plus beta 1 hat x minus x bar, just with some definitions in algebra. And then I can write out the variance of y hat as the variance of y bar plus now the variance of b1 hat, and this x minus x bar pulls out as a square. And we have a covariance term which turns out to be 0 by some algebra shown here. So in conclusion, we have a formula now for the variance of y hat. So just to be totally clear here, in this formula, the x, so this x right here is a particular x, and this y hat here is the point on the regression line for that x, right? So here's a picture of what we have. And so I have my particular x. So, and also to be clear that this particular x is already part of my data. So this isn't some new x. This is an x that is part of my data, x1 to xn. Okay, so with this x, what this expression is saying is that I get a confidence interval for e of y, a confidence interval for e of y, which is this interval shown here. And what we're going to do next is we can write a confidence interval for the Tyche line, e of y, and a 95% CI for e of y is given by this formula here, where the standard error is exactly what we computed above here. So, oh, and I just wanted to point out here that notice that the variance is minimized when x is x bar. So, so at the point of averages, we get the smallest error band. Okay, next we have the I want to talk about prediction intervals for a new observation. This is not in the book because it's too Bayesian of a concept for our book. So a confidence interval for a random variable is called a prediction interval. For us, we've talked about confidence intervals for parameters, which in the frequentist framework is a constant known to Tyche. In the Bayesian framework, it's often a random variable. So confidence intervals for random variables are called prediction intervals, and our new observation is a random variable. So you give x n plus 1 and you get out y n plus 1 from your experiment. So we're going to find a 95% pi for y n plus 1, and so this theorem here tells you what it is, and notice that it looks exactly like what we just saw for y hat, except that I'm sorry, for e of y, what we were just talking about, except that we have this extra 1 here in our standard error. So this fattens up our error bands. So here's a picture of what we have. So now you take a new data point. So this is an x that hasn't been used to compute your regression line. And if you want to make a prediction for what e of y n plus 1 is, so the corresponding y on the Tyche line, then your error band is going to be a little bit larger than before, as shown in purple here. So the proof of this basically comes down to the fact that the variance of the residual for your new observation is larger than the variance of the residual for your the variance of a residual if your data is an old data point. And I think I explained this pretty well here. You can see that what's necessary here to get the larger variance is that that your y n plus 1 is completely independent of y hat n plus 1, because y hat n plus 1 is on the regression line that was made with old data, and y n plus 1 is completely independent of your old data. So y n plus 1 is completely independent of y hat n plus 1.